Hi everyone. So first, thanks to the organizer for having me. I'm very glad to be here. It's my first time in India. First things like congratulations to India because on Friday, they have the youngest chess world champion ever. So congratulations to India. So I'll be talking about Run-and-Tumble particles, and I'm super glad for the talk of Ona because this was a perfect introduction to my talk. So then I can skip all the introduction. And okay, the thing is here. So following Sridip's talk, I should have put some exact thing on the title because all the results I'm going to present are going to be exact with like zero approximation or nothing. So I'm sorry, I have a very bad writing, so everything is written in caps, so it's readable. I'm really sorry for that, but anyway. So the goal of this talk, what I would like to explain to you is that we try to find a way to find some kind of formalisms that helps to build some, so what I call university classes, even if there is no phase transition, but meaning that at some point, so as Ona explained, it's very important to take into consideration the microscopic details. The problem is that if you work with microscopic details, very quickly you can get lost in a huge zoology. Like if you change a little thing, then it may actually change all the computation and you need to redo it again and again. So the idea here is to try to bypass that and say, okay, if these microscopic details belong to some kind of class, then your steady state is going to have this explicit expression and you don't need to do any computation. And because this is actually the picture we have in passive particle system. In passive particle system, we know that for any system, the steady state is going to be a product measure that is going to be separated into the Boltzmann distribution for the positions of for the configuration and some Gaussian for the dynamical variables. Then once we have the Boltzmann distribution, we can say that the dynamics is supposed to be reversible, and then the goal is to find some Markov kernel K that is going to satisfy the detailed balance. If you go to the passive world, it's reversed. What you have is if you have a Markovian process, so it's a case if you have active Brownian particle or Run-and-Tumble particle, and in this talk I'll be focusing on Run-and-Tumble particles. And so at the difference of the active Brownian, the noise is only, like the only stochastic the component is in tumble. So Run-and-Tumble particle follows some ballistic transport, and then at some point, following some Poisson process, it will change this ballistic transport. And so most of the time, it will just be changing the direction of the translation. So this type of dynamics can be put under a Markov kernel K, but the problem is that this Markov kernel will be non-reversible. And so instead of having this very neat detailed balance condition that force the steady state to be of this form, we have this global condition that makes it hard to retrieve the steady state. All the more when we have this type of interaction. So German interaction is one of the simplest interaction you can put between RTP. It just means they are hard cores, and as they collide against each other, they will keep pushing along their velocities, and so they will stay stuck. Okay? And it's a bit like hard spheres in passive particles. It's way harder to treat analytically than soft spheres because you don't have any softness to deal with. So here, that's the type of interaction I'll be considering in this talk. So yeah, so retrieving the steady states, it's hard. And the problem is that it can show very interesting behaviors. So I'll be a bit fast because Ona did a super job at showing you some very nice behavior, but you can have some phase separation, some clustering, or you can have some obstacle pumping where, depending on the asymmetry of the obstacle, you don't have the same density of particles on the left here or on the right. And here what's interesting is that here it's also a question of boundaries. It's like your particles, they go crash against the obstacles, and then they flow along this obstacle, and then they're out. And so with the jamming interaction here in the obstacle pumping, we can see that there is some fundamental interaction between these ballistic flows and having some kind of hard boundaries in your system. Okay, so usual question is like, can we put this pi steady state into some kind of product measure or not? Is there some effective Boltzmann distribution? Some more interesting points linked to the microscopic details, like what is the true impact of reversibility breaking? Okay, because it's not because you break reversibility then you're going to be in a very strange non-equilibrium world, and you can actually have some non-reversible process that are going to leave this Boltzmann distribution invariant. To all that, the question is the one: can we define some classes that are going to be universal for a given set of microscopic details? The problem is that the main theoretical approach are mostly based on coarse graining or relying on some kind of local equilibrium, so a bit like what Tridib explained. And the problem is that with this type of approaches, the microscopic origin of effects are lost. And so the question is like, could we try to derive exact results directly from microscopic details? And so, as Una explained, it's not so easy, and there is not so much, not a lot of results on that. And so you cited a few papers I'm just going to cite. Actually, no, there is one more. So the exact result paper I know, so correct me later in the discussion if I'm wrong. You can have some active lattice gases approach that leads you to have some hydrodynamic large-scale limit. You can have the work of Sloman and al., where you put two RTPs in a lattice, 1D periodic lattice, and you do some genetic function, the discrete master equation. Or then you can have a continuous master equation, but then you need to add some thermal noise to achieve that. The problem is that for both these models, this approach is very important to have a discrete models, which does not seem right when the real interesting physics is going to be the interaction with boundaries, okay? Because then your discretization is going to be very hard to make scale with the physics of the problem. And then if you add some noise, then you are going to change the physics. And this type of strategy are quite common. So you try to smooth out your problems either by space discretization, thermal noise, or even some soft potential instead of considering jamming interaction. And so the question is that could we find some formalisms that directly handle the real challenges that are at end, meaning the boundaries condition, having continuous space and time modelization, and having formalisms that can generalize well to any microscopic change. And so here, that's what I'm going to explain. And so I'm going to consider n equal to RTP model with jamming interaction on the 1D torus. So this is a model of Sloman and al., but it is generalized to any tumbles, because the point is to see, to define universality class that are going to say if your particles tumble this way, the steady state is going to be this way. If it's tumble another way, it's going to be in another class. And typically, like the two types of model people like to see, it's called the instantaneous tumble, where RTP can jump from a velocity of 1 to a -1, given some Poisson rate, or the finite tumble, where RTP, before flipping its velocity, is going to a 0 velocity state. Okay, so it's like the little bacteria is moving, then it will go to 0 and then change direction at some point. So here, the main point is actually a new analytical approach, is to use the formalisms of piecewise deterministic Markov process, which actually are quite known in probabilities, but I didn't encounter a single physics paper that know them. So I'm going to explain what they are. And the point is going to exploit all the possible symmetries. So in this type of 1D torus, with the same RTP, you need to exploit the particle distinguishability, the space homogeneity, and the periodicity. So why these methods have some, it's very likely they are going to work. That's because this type of piecewise deterministic Markov processes are the stochastic processes that are generated by some very efficient, non-reversible Monte Carlo algorithm. And it's like they are generating some kind of artificial RTP that is going to explore the Boltzmann distribution. But then, in the end, the distribution is fully the equilibrium one. And the whole thing is that, the whole point is that if you if you retrieve the equilibrium distribution in the end, that's because when you have an event, when you're reaching a boundary, you're doing some kind of change direction that is following the fundamental symmetries of your system. And here, the point is that if it is not the case with this RTP system, the question is that what is the symmetry that is broken when they are jamming that makes it that, in the end, the steady state is not the expected passive equilibrium one. Okay, and the point is to characterize the steady state. So I think I need to be way faster than that. Okay, I'm just going to say the outcome. Okay, so first I will explain this PDMP characterization, then how do we formalize the invariance condition, and then explain what are these universality classes. And if I have some time, I'll talk about some mixing times result in the end. This is the RTP, so it's following a ballistic flow that is just a translation according to some velocity v. This velocity v is resampled at the event time following a Poisson process, following some kernel. And it's, in the end, yields you this type of dynamics between run and tumbles. A PDMP is doing the exact same thing. So this was all formalized in maths by Davis in the late 80s. And it's just a Markov process that has some ballistic flows, okay, following this phi flow. The velocity here is a resample according to some Markov kernel at some event times that is following some Poisson process of rate omega. But the nice thing is that, based on this mathematical work, we know that the invariance of this type of process is completely constrained by the condition that the total variation you put on any test function f must be 0 in the steady state. So here A is called the generator, and it is the infinitesimal change you do to any test function. And so here what change you have? You have the transport along the flow phi, and you have the change of direction. This is the dynamics in the bulk of your domain. Then, if you have a boundary, okay, so here I'm following my little RTP dynamic there, but then I encounter some wall. Here, to have a complete description, you need to define some boundary Markov kernel that is going to redirect your flow. And so here for the RTP, the idea is that the bulk here is going to be the free run of the particles, and the boundary is going to be when they jam against each other. So if we now look at these two RTP problems, so we have the bulk dynamics, where the particles are free, we have the jamming, and then we have, so when they jam, then they will have internal tumbles until they are in a velocity state that allows a separation. And so this velocity state that allows separation, that's when they re-enter the bulk. So here the question is how to encode other system symmetries. And the answer here is quite simple. It's to consider the distribution, the evolution of the interdistance, the periodic interdistance. And here, so I'm going to parameterize my system with the interdistance. Here, a variable nu that is either -1, 0, or 1. And just telling you if you're decreasing the interdistance, -1, the interdistance is staying the same, or +1, the interdistance is increasing. And then S is just a parameter that is monitoring at which speed you are changing this interdistance. And so in the end, as was done in previous works on 2 RTPs, this type of 2 RTP system, you're back to an effective single RTP. So if you want to know the PDMP characterization of that, so here it's like my effective single RTP between 0 and L/2, because this is a periodic interdistance. And when you're in the bulk, then you're following this free transport, and then you have the tumbles, according to this Markov kernel Q. The good thing is why I put this new parameterization is that because you have the particular indistinguishability, you have the isotropy of Q. And that's because the difference between having the transition from nu S, nu prime S prime to minus, compared to the one of minus nu S to minus nu prime S prime is the same thing as looking at your system from above or from under. So it's the same thing. When you have the jamming, then your generator is just the tumbles because you're stuck. And then when you have the periodic boundaries, then it's like from this interdistance, it's like just flipping its velocity. And that's because here, if you look at the 2 RTP, they are going this way, but once they are past this L/2 distance, then they are decreasing the interdistance again. So here, I mean, there is no choice or whatever. It's just the formalisms. So now let's look at this invariance condition. So the invariance condition is like, okay, all the incremental change done by my generator should go to 0 when I'm in the steady state. And so here, this omega is a full state. So that's the bulk and the jamming. So in the end, it goes to that. So here you're doing the integration over all the possible states. And here you have a partial derivative. So the idea is to do an integration by part. And if you do the integration by part, then the integration by part will link your bulk to your boundaries. That's the point of integration by part. And these boundaries are what? They are the jamming and the periodic boundaries. And so in the end, that's why you end up with these three conservation constraints, which is that in the bulk, the tumbles and the transport compensate each other to a given probability mass in a given configuration. In jamming, it is the tumbles that is going to compensate the transport into and out of jamming. And then the periodicity is just a symmetry condition on pi. And so the important thing to understand is that in the end, these conservations is just a balance between the run-and-tumbles and some boundary terms. So now let's look at this bulk equation. So when you look at this bulk equation, a very natural quantity to define is this tumble measure that is going to be left invariant by the tumbles. So it's like if you look at the free particles, what is going to be stationary distribution in terms of velocities. If you define that, what you can see is that, okay, if I see this equation and I want to look at some uniform solution, you find actually that the only uniform solution you can find is actually the passive one, meaning that it is a product measure with velocity stationary distribution times the uniform distribution. So this is like having some kind of passive particle. Then you say, okay, can I have a solution that is a product measure and it is not the trivial uniform one? And actually, if you plug that in, you find that, again, it is only the uniform distribution. Then you say, okay, I just want one that has this kind of detailed type of symmetry between the plus and minus regime of the interdistance. And if you plug that in, the only solution is, again, the uniform distribution. And so here, the important thing is that it is not the bulk condition and the non-reversible transport in the bulk condition that is making all these nice phenomena emerge. Because if you look at the bulk condition alone, the uniform distribution is going to be the answer. And so the real physics is actually in the jamming, in the boundaries. And the non-equilibrium features, it's the idea that non-reversibility push you to the boundary. And there you see the physics. But it's not the non-reversibility itself. And so if we look, where is that? Yeah, okay. So now if we look at this jamming condition, we can see that these terms here forced to spend a finite amount of time in the jamming configuration. And so here you're going to have Dirac mass, which is not a physical, equilibrium feature. Then here you have the boundary term, and this is going to impact what's going on in the bulk. But if you don't have this condition, this one, the jamming condition, you're not going to see any non-equilibrium features. And so in the end, these non-equilibrium features have everything to do with the boundaries and not a lot to do with what is going on in the bulk. And now the question is that can we classify such impact? And the answer is yes, and I need to answer in 2 minutes. And the idea here is like, okay, let's try to find some kind of general relationship. And if you look at dynamical process in equilibrium systems, you have either data balance or global balance. The point is that global balance is some kind of conservation of the probability flows. And so here, if you have a passive systems, the necessary global balance equation tells you that all the probability flows that flow into some OR configuration are balanced by the ones that goes out. And then you can have a stronger condition, which is the detailed balance, that between any two pairs of configuration, you have these things. Do we have the same thing for non-equilibrium systems? And the answer is yes. Here, we can understand this active RTP system as being controlled by some Markov kernel K, but, as instead of being controlled by some Markov kernel K, what is pushing the probability mass, that is going to be the transport. And here, the idea is like to integrate the condition over the dynamical velocities to end up to try to have some relationship on this transport phi. And what you get is that when you do this integration, you get this relationship, And when you put them together, you find some kind of active global balance that is telling you that all the ballistic flows into a configuration are equilibrated by other ballistic flow out. And then this is some kind of global condition, and you can define some kind of detailed, more stronger condition on that. But here's the difference compared to this type of recyclable passive system, is that here it's more like on the ballistic transport. And this, if you remember, that was one of the conditions that plugged in the bulk that ended up always having a uniform solution. So now the question is that, can we classify the behavior of this 2-RTP system just by the condition, is this active detailed balance broken or not? And the answer is yes. So to remember, if you have just passive particles that are just hardcore repulsion, you expect to have some uniform distribution in the bulk. Then if you have the active detailed balance, detailed jamming class, where this detailed balance is satisfied, you find a uniform product measure, but you have this direct mass in jamming. So this is the only non-equilibrium feature you have. But then if you broke this detailed balance, then you're breaking the uniform distribution. And in the bulk, you're going to have still some kind of uniform distribution. I forgot to put the uniform here, plus some relaxation. And this relaxation, so in here, why do we still have this type of uniform term? That's because it is imposed by the periodicity, where you are actually recovering this detailed symmetry. So here, okay, this is just a slide to say that we have other explicit solution, everything is explicit. And the same for the global jamming. And I'm going to finish very quickly on that. Because, okay, it's very nice to have that, but then it would be nicer to have an explicit expression for gamma. And the point is that this gamma is actually only for, being ruled by a first order ODE that is set by the bug condition, and just having some kind of boundary condition because of jamming. And here, that's the only moment where I'm making some kind of assumption on my velocities variable, where I assume they are discrete, but they can be any number, any things. But here in the end, this CB gives you some ODE, one order, but because of the interesting symmetry of this B matrix, in the end, you find this second order relaxation type of equation. And this, in the end, depending on the spectral structure of M, gives you some kind of catenary-like relaxation. And you have this type of relaxation. And this is actually not surprising. That's because if you look at this type of RTP, so this is a solution you expect to have. Here, in the middle, you are restoring the detailed jamming symmetries. But here, the jamming is some kind of boundary condition that is away from equilibrium. And so you have this analogy where, so remember the catenary is like when you have a rope, and instead of putting it on the floor, you elevate the two boundary, the two extreme ends of the rope. Here it's a bit the same thing. It's like boundary conditions are away from equilibrium for the rope, the cable case, but also for the RTP. I'm going to finish quickly. And then, so the rope or the point distribution wants to relax. And then you have the competition between different effects. So for the rope, it is simply the weight force that wants the rope to go to zero as fast as possible. But then the problem is that you have some tension of the rope or some rope lengths that say, okay, we need to go to zero, but we cannot do it in an extreme manner. And here it is the same thing for this priority distribution. It's like the tumbles or the weight force that want the distribution to relax to this uniform distribution. But because it is a priority distribution, it is normalized to 1, and it acts as some kind of length rope. And then the tension can actually be understood the runs can actually be understood as some tension. And I'm going to finish there. So we have also exact results on the time it takes you to go to equilibrium, where you can have a ballistic or a diffusive regime, depending on these parameters. And here is the conclusion, so I'm going to conclude very quickly. So here I hope I convince you that this PDM approach is very neat to be super sharp when you're dealing with this type of some non-reversible flows in some bulk, and then some very hardcore boundary type of condition. Then I think this active detailed global balance is actually more general than this 2RTP problem. And I like it to, I think it's going to show up in other problem. And then the big question is like, okay, 2RTP are nice, but NRTP is better. And we actually have some results for more than 2, and then for 3 actually it's very simple because you have the same type of symmetrical argument. Okay, and thank you for your attention.
Long live India and France friendship.